All right, we are back and we are going to talk about one of the key material properties of polymers, which is the glass transition temperature, or TG. So we discussed non-crystalline polymers, the glass transition temperature, if you've seen it in other classes, this rubbery to glassy transition. So you'll typically deal with polymers that are interpenetrated, Gaussian coil, that's how you model it. So when we say interpenetrated, basically they're kind of entwined with each other, but they're not fixed, so they can slip past one another. So it's in this kind of random state. Now the glass transition temperature is the transition from a fluid state to a more glassy-like state. So a glass has short-range order. It lacks long-range translational order. So basically, you don't have these translational fluctuations. You don't have long-range order, not to the extent of a metal, obviously. So you lack those frustrations. So you're kind of kinetically trapped in this glassy state. So it's not the long-range order we expect from a crystal. But the glass transition temperature, you could break it down as a competition between the available thermal energy and the intermolecular bond energy. So a glass and the rubber, we can basically break it down into these two sections. So in terms of the TG, higher temperature is going to be that for the rubber, lower for the glass. If I have lower KT, lower temperature, I'm going to be in a glassy state. If I have high temperature, high KT, I am going to have my temperature is greater than TG, I'm going to be in the rubbery state. Temperature less than TG, I'm going to be in the glassy state. So in the glass state, my epsilon ij is greater than that of thermal energy. So I'm not going to have movement or fluctuations. But in the rubbery state, I have enough thermal energy to obtain some type of long-range collective motion of about 30 monomer units. So that's kind of the definition. So it's this competition between, as you increase the thermal energy, when you transition from a glass to a rubber, you basically reach a point where my thermal energy breaks or actually is larger than that of those intermolecular bonds. Intermolecular, not intra. We're not breaking covalent bonds. We are breaking those intermolecular interactions, H bonds, some of these things that allow the polymer essentially to effectively wiggle around. So we're going from the frozen state to now we can start to, again, wiggle a little bit. The glass transition temperature is closely related to the relaxation time of a polymer. So this tau prime is the relaxation time of a polymer, and it's how long it takes to return to equilibrium after some perturbation. So I use this example of I attach a polymer to a box, I apply some perturbation by pulling those box, and basically we want to see how long it takes for it to respond. And one way we could characterize this is using what's called the Deborah number. So each polymer has its own characteristic relaxation time, but we could also change T, the time of the experiment. So that characteristic relaxation time will depend on the structure of my monomer units. It will depend on the rigidity, molecular mass, lots of different factors will affect essentially that relaxation time of a particular polymer. But again, it also depends on the time scales of our experiments, time, temperature, equivalence. So we can think of basically classifying two separate scenarios. So if I apply perturbation, and let's say that the experimental time is such that it is much, much greater than the relaxation time scale of my polymer, and I have a DE that is basically much, much less than 1, a Deborah number that's very, very low, you can basically say that that polymer instantaneously responds. So basically it basically relaxes back. If it instantaneously responds, that is characteristic of a liquid type response, a liquid type material. So we can say it flows. That is a liquid type response. It's a viscous type response. Actually, it's liquid. It's not really even viscous. But it is viscous. But anyways, you could also consider. Oops, let me zoom in a little bit here. You could also consider the opposite response, where my relaxation timescale is much longer than my experimental timescale, and thus my Deborah number is much, much greater than 1. So this is characteristic of an elastic response. Basically, I'm not giving my polymer enough time to relax back, so I'm going to pull on that polymer chain. That's my instantaneous, it's the elastic response. So as I pull and that polymer is not able to relax back, strain energy is going to build up in my material. It's going to get that elastic response, and it will thus behave elastically. If it's elastic, that is a solid type response. So that's kind of the key aspect there. So my Deborah number is much, much greater than 1. I'm elastic. So my Deborah number is less than 10, but if it's greater than 0.1, this is where most of our polymers lie. So that's a viscoelastic response. So that's where you're going to find most of your polymeric materials there. Again, relaxation time depends on structure, connectivity of the monomers, interactions, H bonds, et cetera, flexibility of the backbone, lots of different factors there. So that's a topic for another course, our polymer course, and timescales as well. So next time, we are going to get back to glass transition temperatures and see how the molecular structure depends. So we are going to, actually, we will continue this video, actually. So let's get back to our glass transition temperature. So remember, it's not really a thermodynamic transition. It's, arguably it's a second order thermodynamic transition. And we could actually measure the glass transition temperature if we run a DSC experiment. You'll notice, again, endo up, exo down on the y-axis. You'll see a second order phase transition will see a different, basically a change in the slope there. Whereas a first order phase transition, like melting, if we're to measure heat flow versus temperature, we see a discontinuity instead of a change in the slope. That's going to be your melting temperature. And remember, polymers, every polymer is a TG. Not every polymer has a melting temperature. If it's a semicrystalline polymer, it has a melting temperature. If it's amorphous, it will not. So it is kind of this kinetically trapped transition. And again, we need enough thermal energy to get around 30 monomers moving. And actually, you could change the glass transition temperature kinetically. So depending on the rate at which you heat or cool a system, you could actually change essentially that glass transition temperature, their relaxation. Again, a little bit beyond the scope of this class. Next time, we're going to get into how TG and monomer structure affects the